What's up, you guys? I'm Dan. This is Frugal Not Cheap, and today we're going to be talking about Tesla's AI Day. So as I'm filming this, it's just about less than a week since Tesla AI Day happened, and Max. Had a chance to kind of see what other people are saying about it, and I thought that there's really an opportunity for me to present things a little bit differently. What I'd like to do is I'd like to go over the greater context, just take a step back from AI Day. Then we'll dive into an actual breakdown of the event, what I think were the important things and the lessons that we learned from the event itself, and then also finally look at the implications for Tesla and in some ways society as a whole as well. I will also say a couple of things before we jump in. One is that I am a Tesla shareholder. Obviously I'm long the stock, so that's something that you should know. Also, I'm crazy about the company. I try to be as honest as I can and talk about the things that are not as. And the other thing to point out is, my background is in economics, and I work in the financial world as an options trader. I'm managing over-the-counter options book, so I'm looking at it more from that kind of an angle. I'm not, although I know a little bit of computer language and some basics, like I messed around in Python a little bit, but really I'm not an expert at that stuff. There's a lot of the jargon in AI Day that I actually don't know or don't understand very deeply at all, besides more than a very surface level thing. So I'm going to do my best not to touch on that. I'll say that I'll probably make mistakes. This is just the best of my understanding, and I'll, hopefully I keep myself to within the domain of things that I know, and so then I won't make a whole lot of mistakes and lead anyone astray. So that's going to be my effort. The other thing is I don't know how long this video is going to be. All right, so where to begin? Again, I think it's really important that we take a step back and look at the context. And I'll kind of reference back to my thoughts on the billionaire space race video that came out recently. The whole point of that video was to point out that the narrative that you see in the media might not necessarily be the only way to look at things. And in fact, maybe if you dive deeply into the details, it's really not at all an accurate way of looking at things. So in that video, I tried to make the case that it isn't three billionaires competing in each other for I don't know, points or whatever, status or what have you. It's not like that at all. It's much more complicated, and at least in Elon Musk's case with SpaceX, there is a much more altruistic goal in mind. And so that's, I think, where I'd like to start. Is Elon Musk is a man who has faults like any other man. But there's some pretty neat things about him that you may not know, and that's that essentially everything that you've seen him do has been geared around solving some kind of a problem, things that he thinks are a real issue. And the crazy thing is he's then had the risk-taking and vision and guts to go after trying to do something about those things, being fully cognizant that he could fail. So what are those things? And if you want to learn more, by the way, there's a great, I guess it's a blog called Wait But Why. So you can Google that, Wait But Why. And there's a series on Elon Musk that, we really kind of dive deep into this stuff. So the things that he saw as really issues, or one, of course, the climate and sustainability. That's where Tesla comes in. So a lot of people think of Tesla as being a car company, but it's far more than that. The idea is to push us towards renewable energy, in other words, electricity, which we're increasingly generating from renewable sources like wind and solar. And then, of course, batteries, right? You need to be able to store that energy when the wind's not blowing and the sun's not shining. Tesla is one, pushing consumption towards electricity, which is then renewable, then also addressing the battery, the storage problem, and then also addressing the production problem as they're rolling out. There was Solar City that they acquired that was tangentially related to Musk or his brother. Now they're working on this solar glass tile product, which looks really good, generates solar, and lasts a very long time. So it seems to be a really good, good premium roof product that's out there, and they're having some trouble scaling it up and scaling up the installations, but hopefully they'll get there. So that right there already addresses a lot of the problems towards climate change. And of course they're expanding. They're going to work on the semi, which is going to reduce a lot of emissions from transportation, where we use a lot of diesel right now for logistics. And who knows, they may tackle air travel, more likely regional rather than international travel, because of the weight to energy constraints in batteries, even as those improve. But anyway, so they could tackle, there we've got like the whole chain, right, of production, storage, and consumption of energy. And they're getting into the home space as well. You can have those power walls in your home, but they're probably going to get into HVAC. So anyway, that's a big piece of that puzzle in terms of climate and sustainability that's being addressed by this one company. What were the other things that Elon was worried about? Well, he's also worried about AI. So that's artificial intelligence, and not the I don't know if you remember in the 80s, everyone would slap on turbo on things to make it cool, right? Like, there was this thing, turbo. And now companies slap on AI onto anything to make it seem cool, right? It's a branding thing, and it doesn't really mean anything. There's machine learning in a very narrow scope, and AI. But the threat that Elon talks about is generalized artificial intelligence. But the threat is that if you have a hyper-intelligent synthetic consciousness, it is very different from a human, because and this stuff is my thinking, not Elon's. We have in our DNA, in our makeup, a lot of instincts that are very, very powerful. We have an instinct to procreate and protect. All kinds of things are instinctual. We like to think of ourselves as very, very advanced, but if you look at the complexity of behaviors in animals that can be instinctual, it's pretty incredible. So if nothing else, at least should give you pause to think, well, how much of my behavior really is this evolved ape thing, and how much of it is instinct, and how much is it directed by instinct, if nothing else. But if you have a synthetic being that doesn't have the chemical part of it as well, and this instinctual part of it, doesn't feel pain, doesn't feel love, doesn't feel any of the things that we have, all these things that really create bounds for our behavior and thinking, if you think about it that way, right? It won't have that, and there's no reason why it should care about our existence or the existence of anything. And if it's able to become, rapidly much more intelligent than we are, then there's all kinds of scenarios that you can think of which are terrible for us, which lead to our extinction or enslavement, or maybe just being kept as pets in some kind of a way. Anyway, very dark. We've all seen Terminator and all these other kinds of movies, right? So that's a possible future if you don't get it right. Whereas in Isaac Asimov's books, which Elon Musk is a fan of, by the way, I loved them growing up, they have these 3 laws of robotics designed to provide those boundaries for the behavior that robots can have. And of course, there's all these problems, that they have in these corner cases where those 3 laws don't quite work, and it's very entertaining. But the point is that it was necessary to bound that behavior, because it's a huge problem if you have synthetic generalized AI where the behavior is not bounded. So that's why Elon Musk started 2 companies. One of them is OpenAI, which was, supposed to build really advanced AI. They did stuff with computers and a little bit with also like object manipulation with these robotic arms and hands and stuff. But I don't know, they kind of went in a weird way, I guess, and they split ways from Elon. And then the other company, which you may have heard of, is Neuralink. And the idea here is if you can't join them, beat them. If you can't beat them, join them. So the idea is to develop this brain-machine interface so we can be at least hooked up to the AI and have some kind of a hopefully symbiotic relationship, right? It's the hope there. And then having given up on OpenAI, I think over the past few years, Elon has seen that he has a great opportunity to use Tesla as the place where he develops AI in order to have a way to shepherd it. Not just him, of course. When I say Elon, I really mean Elon and his team. So that's really, I think, the context for this Tesla AI Day, is trying to push forward artificial intelligence and shepherd it. Elon has called for regulation on AI to try to keep those bounds there so we can prevent a really bad outcome. And I think that if he has a company that's at the bleeding edge of it, then he can, try to help make those kinds of things happen. Try to keep a good outcome happening. And then before we move on more into AI Day, then I'll just point out, SpaceX, of course, is designed to make humanity multiplanetary in case something bad happens to this planet. Just as the dinosaurs, how it can work out when you have all your eggs in one basket. And then there's the Boring Company too, which could help alleviate congestion and traffic, which is a horrendous waste of our time and very dangerous as it is right now as well. Could be useful also on other planets and that kind of thing. So all these issues that his ventures are designed to solve, but they go about doing that not in some really silly way where they just burn a bunch of money trying for a goal and then run out. They put out products that people like and love, and then they're able to then continue on their mission, right? So really, really cool. And then I totally forgot about Starlink. That's amazing too. All right, so I think that's really the context for it, is trying to shepherd artificial intelligence, and the path towards getting there, towards this generalized AI, is to develop more narrow forms of AI. And the full self-driving, which is really the problem of having a car, you have two outputs, right? You have the steering, and then you have the speed, the acceleration, and the braking. So I guess those are three outputs of the code, which are inputs to the car, which makes it do its thing. The problem is trying to understand the world and what's going on, and have a goal, and then spit out what exactly should be those outputs in any moment for the car, and then you've got a car that drives itself. So again, it's pretty narrow, but what they've learned over time is that actually all kinds of weird things happen on the road. So it's not like a video game like what OpenAI was doing with Dota. It's really more complex, and so it really needs to have an understanding of what things are that's much broader than you might think. Also, all these rules for how to interact with other cars and with the environment, and then even what's comfortable for the passengers in the car. So it's a pretty complex problem, and they've been trying to make headway. And there have been many points where Elon Musk has stated publicly that he thought that they were very close to solving the problem. He's expressed a whole lot of confidence going back all the way to 2016. There's this long list of places where he thinks, absolutely we're going to have this problem solved very soon. And what happened is they would reach what he's called a local maximum. So when you solve an optimization problem, let's say you have a solution surface that isn't just a convex thing where you can just find with your budget constraint, find the global maximum very easily, right? What's the absolute best thing that we can do? How do we solve this problem? You can have solution spaces that have little like hills, and then a bigger one, and then a valley, and so it can be more complicated. And if you're trying to solve that problem starting from here near this small hill, you might find the top of that hill and be like, okay, we were able to achieve this, but it doesn't do us any good to reach the top of the real peak over here. So that's the problem with a local maximum versus a global maximum. And frankly, looking at the evolution of the FSD program, which we get a really good sense of in this video, I'm actually surprised at how naive the thinking was that the initial versions could solve the problem. But I think what we're going to do now, it's probably a good place for me to jump on, and then I'll be at my computer looking at the video, and we'll go through AI Day, and I'll give you a little bit more of the breakdown of the actual event. So that was the context. Now we'll do the breakdown of the actual event, and then we'll wrap up with some of what I think are the implications coming out of this. One of the things which is pretty obvious, so obvious that I forgot to mention it, is that, of course, the FSD full self-driving problem itself is designed to alleviate two things. One is that, traffic fatalities and injuries, which are a substantial problem globally. And then the second is, of course, just the lost productivity that we have while we're sitting at the wheel and stuck in traffic. Here is just FSD happening. Yeah, so that was just the end of the little clip before the presentation starts. And the point there is, look, we've had cars that can basically do the highway part. Highways are easy because there's no turning. You're just going straight on a road. It's got lanes. Everyone's going in the same direction, and all you've got to be able to do is, change lanes, be aware of traffic in front of you and its speed, and modulate your speed accordingly. So relatively simple problem. We've had that going on with Teslas for a long time. And then in cars that have the full self-driving computer, which are all the Model 3s and Ys and all the Model S and X produced after October 2016 or so, they have, the Model S and X can be upgraded to the FSD computer, which I've done in my car. It's a 2017 Model S, probably from the first part of the 2017. Anyway, it can change lanes, so that's a pretty cool thing. Also, it's keeping track of traffic on either side, and then seeing when it's safe to change lanes, and then it'll make the lane change, and so on and so forth. But the big difficult part of it is driving on city streets. So here we have stop signs, we have yields, we've got roundabouts, we've got U-turns, we've got unprotected left turns, which are turns where you don't have a light that allows you to be able to take the turn safely, right? You've got to look out for other traffic and that kind of thing. You've got parked cars, you've got pedestrians, you've got dogs, you've got debris that's fallen off a car in the roadway, you've got motor. It's just really a much more complex scenario. Parking lots also, so all this stuff. So that's really what they're working on now. That's the big challenge at the moment, is to get the car to be able to handle those things and really get from one destination to another all on its own.
It is much more than an electric car company. That we have deep AI activity in hardware, on the inference level, on the training level, and basically I think arguably the leaders in real-world AI as it applies to the real world. And those of you who have seen the full self-driving beta, I can appreciate the rate at which the Tesla neural net is learning to drive. And so this is a particular application of AI, but I think there are more applications down the road that will make sense, and we'll talk about that.
All right, so I think at this point it's a really good place to back up a little bit and give you a sense of what's been going on at the company. And yeah, I haven't really seen this in other videos so much. So for those of you that might be completely new to this whole thing, a while back, Tesla worked with a company called Mobileye. They had their sort of autopilot solution, right? They can do the traffic-aware cruise control and some of the basic features here. And when we say autopilot, it doesn't mean like let go and the car does whatever. It's more like the car keeps doing what it's doing safely. Just like an airplane, you put autopilot on and then it maintains course, right? It's kind of the idea. But it still needs supervision, and anything more complicated, beyond its domain of competence, then you've got to jump in. And so it's the same thing with the autopilot. Tesla was working with Mobileye for a while, and they had this what we call AP1. And then they realized, we've got to bring this in-house and vertically integrate. Tesla's huge for vertical integration, and so they brought a guy, Jim Keller, who helped design some chips for AMD, brought him in to develop their in-house full self-driving hardware. And this is the thing that came out in 2016. And at the time, this sort of system, this board, had sort of two processing units essentially, and the idea was that these two things would run in parallel, so you'd have redundancy. Like you would obviously only one would tell you what to do, but it would check against what was the result from the other one and that kind of thing. So you'd have a lot of safety there. And so this is a computer that you stick in the car, and it runs and makes all the decisions, right? So when in the video, they're going to talk about two different parts, like in AI Day. There's the part of like training the neural net, and then there's the actual like a test time, they call it, when the car is actually feeding in the data from the cameras and everything else that all the other data it has, and then running on the computer that's on board in the car, and then making decisions about what to do. That's sort of that's one part of it. And then there's also the part that is training the neural net. In other words, developing the software that gets updated on the car that that it uses in order to run to do all this stuff, right? So there's really two different things. It's not like some people might think that. So the car itself isn't learning on its own. So it's not actually developing its capabilities for self-driving based on its past experience. That's not where the training happens and all the learning happens. It just runs the program. Where all the learning happens and all the training happens is at Tesla, and then they ship out over the software updates, the new version, and then the car just runs on this new version. So that's really more the way to think about it. Is all the learning is happening in-house at Tesla, and then your car just gets software updates and then runs on that, and it's using this FSD hardware, which is currently at version 3.0 in the car, is version 3 hardware. In order to run that. So hopefully that's helpful to give you a sense of how that works. So now I think we'll skip over Elon's stuff and we'll get into Andre, who's head of the vision team.
My name is Andre, and I lead the vision team here at Tesla Autopilot, and I'm incredibly excited to be here to kick off this section, giving you a technical deep dive into the Autopilot stack and showing you all the under the hood components that go into making the car drive all by itself. So we're going to start off with the vision component here. Now, in the vision component, what we're trying to do is we're trying to design a neural network that processes the raw information, which in our case is the 8 cameras that are positioned around the vehicle. And they send us images, and we need to process that in real time into what we call the vector space. And this is a 3-dimensional representation of everything you need for driving. So
okay, there's a lot there, and I'll try a little bit to unpack it. So neural nets are a little bit like you've got a complex network of basically neurons, synthetic neurons, that kind of do one thing, and then everything is done probabilistically. So because of that, there's a lot of math involved, mostly matrix math. And so that's why currently a lot of the processing is being done with what are called graphical processing units, GPUs, basically video cards that you play video games with. But what Tesla's done with Hardware 3 is they developed their own in-house chip that's really, really good at doing matrix math at the level of complexity that they thought they would have to do it in order to run the neural networks that they envisioned at the time. Obviously, things have changed. Actually, you know what? It's really kind of hard to explain. So I'll recommend, there's a really, really good interview between Rob Maurer of Tesla Daily and James Dauma. I'm not sure on the pronunciation there, but James really knows the stuff in terms of artificial intelligence and machine learning and AI, and so I think that would be a really good resource to learn really what's going on there. So they have these neural nets though, which is basically sort of the analyzing and thinking and decision making part of it, right? Although even that, not all of it's happening here. Andre's just talking about the vision part of it. So it's taking in the input, which is what the camera is seeing, which what the camera is seeing is actually just at any point in time, at any frame, it's just an image, right? And this image is made up of a certain number of pixels. And so you've got these neural nets that can do different things. Like, some of them will be good at detecting sort of the boundaries, like where the pattern of the image changes. And others will do different tasks, as they analyze this image and figure out what's going on in it. Because, for us, we don't really think about it. We just look at the world, and heuristically, our brains are very rapidly, right now I'm looking at a monitor, so I can see this box, and my brain very quickly differentiates this box from the wall behind it. It generates depth. Very, very quickly, it's developing a sense of what are the different objects in the scene. And I don't even think about it, but if you take a moment to think about it, that's what your brain's doing, right? There's a signal. Very much like with the cameras, they're taking in light. That light, crosses and then goes through the optic nerve or whatever to, the processing centers, and there's various of them, and then you come up with what you're seeing. And so that's very, very a good parallel to what happens with the car, is that light goes into the cameras, and then it sends a signal to this FSD hardware, this computer, and then it runs neural nets to process those images. So the next result is they develop what's called vector space. As you're driving along, if you kind of take a quick look around, what you have is, of course, a sense of self in this car. In this video, they'll reference ego a lot, and ego is, of course, ourselves, right? So that's you, and then, of course, you'll have a sense of the road, and it's doing that parallax thing, so you get a sense of depth that way. And then you have the cars around you, and you have a sense of their speed and direction. And as you know, vectors can give you sort of the direction that the thing is moving in, and also how rapidly it's moving in. You could also figure out not only their speed, but their acceleration and deceleration and that kind of thing. But anyway, you kind of have a sense of that, right? I don't know, if you've ever played any kind of a sport, you also have a sense of, where things are around you, who's there, what are the stationary objects, what are the moving objects, that kind of thing. Essentially, those ideas, not the details about, what so-and-so's shirt color is or anything like that, or what kind of, the back to the road thing, not, what kind of car is it or what color it is. Those things aren't really that important for making the decisions about driving. It's just about really distilling it down to this vector space and the basic building blocks that you need to figure out what the best thing to do is. The thing that's really smart about doing that is that you're taking a very complicated thing, because we're not just looking at one image, you're taking 8 images, right? So we've got a ton of data, and there's a ton of data in there that we don't need, again, like the color of cars and all this other kind of stuff. And so you're taking a large data set, and then you're distilling it really into the important stuff, which is this vector space. And once you have it boiled down to a vector space, then it's much more like a video game. And we already know that machine learning and AI are really, really good at figuring out video games. They can figure them out and kick the butt out of humans very, very easily, right? This is something we didn't dream about, a decade ago, but now it's common knowledge they're way better at it than we are. So that's the idea. And then the other brilliant part of it is that if you're making all the decisions in the vector space, then you're always bounded by processing power, right? So if the data that you're using is your input at this stage, right? I mean, sometimes I'm going to use words and jargon that might not be the best word depending on what your background is, right? I might use them more sort of like an analogy rather than this is the word for the thing. But what I'm saying is that for the part of the car program that makes decisions about when to turn the wheel and how far and how to accelerate and all this stuff, where it's going to go, the input part of it, right, to this layer is the vector space. And so it's not that huge data set. It's much, much more compact. And so then you have more compute available in order to make those decisions, right? So the more that you can simplify any part of it, the more that you have available to do other things, right? There's just limited computational capacity that's available. And heck, that's true for you and me too, right? So I think it's really the analogy between us and the car is, in many ways, a very, very good one that's helpful to keep in mind as we go along.
What I find kind of fascinating about this is that we are effectively building a synthetic animal from the ground up. So the car can be thought of as an animal. It moves around, it senses the environment, and acts autonomously and intelligently. And we are building all of the components from scratch in-house. So I'm going to roughly organize this section chronologically. So starting off with some of the neural networks and what they looked like roughly 4 years ago when I joined the team, and how they have developed over time. So roughly 4 years ago, the car was mostly driving in a single lane, going forward on the highway. And so it had to keep lane, and it had to keep distance away from the car in front of us. And at that time, all of processing was only on individual image level. So a single image has to be analyzed by a neural net and make little pieces of the vector space, process that into little pieces of the vector space. After a BiFBN and a feature fusion across scales, we then go into task-specific heads. So for example, if you are doing object detection, we have a one-stage YOLO-like object detector here where we initialize a raster, and there's a binary bit per position telling you whether or not there's a car there. And then in addition to that, if there is, here's a bunch of other attributes you might be interested in. So the XY with height offset, or any of the other attributes, like what type of a car is this, and so on. So this is for the detection by itself. Now, very quickly we discovered that we don't just want to detect cars, we want to do a large number of tasks. So, for example, we want to do traffic light recognition and detection, a lane prediction, and so on. So very quickly we converged in this kind of an architectural layout where there's a common shared backbone and then branches off into a number of heads. So we call these, therefore, hydranets, and these are the heads of the hydra. Now, this architectural layout has a number of benefits. So number one, because of the feature sharing, we can amortize the forward pass inference in the car at test time. And so this is very efficient to run. Because if we had to have a backbone for every single task, that would be a lot of backbones in the car. So here's the kinds of predictions that we were obtaining, I would say several years ago now, from one of these hydranets. So again, we are processing individual images. There we go. We are processing just individual image, and we're making a large number of predictions about these images.
All right, so let's stop there. It was a little bit naive to think that this could work, in my view. They were processing each frame completely individually without a time element to it. Then also, like all of the cameras weren't being brought together in the most efficient way either. But I think what you can get a sense of here is how ridiculously fast all of this stuff can happen. So he said this is just one hydronet, right? So it's just one of many of the tasks that the computer was doing at the time. So again, there's the common backbone, and here's one of the hydranets that's doing certain parts of the task of analyzing these images. But you can see that very, very quickly, frame to frame, right? Which is crazy. In this case, we can see that it's doing it at about 18 frames a second, right, or so. It's able to come up with all kinds of things like, are we blinded? Should we turn the auto high beams on? Is it raining? It's got a high probability here that it's raining. Is the road wet? Is my travel restricted, right? Am I in a construction zone or not? It's also, as you can see, labeling and tagging things. So it knows like there's a stop sign there and there's a vehicle in front of me. And it's got some information about that vehicle as well. And it's doing all of this for each individual frame. And at this point, my understanding is there was no time element to it. So it's kind of like like you had instant amnesia, where every frame it's all new. It's like, oh, let's figure it out, and then another frame comes, it's like, oh, let's figure everything out all over again. And so you can see that that is probably not the best way to solve the problem, because that's not what happens with us, right? We absolutely have a sense of the permanence of things and of keeping track of them, and we have a sense of time. And in my view, it makes the most sense to develop an approach to the problem that mimics what works from us to solve the problem, but only the bare bones of it and not any of the extraneous stuff. But the temporal element is definitely not, in my view, extraneous at all, right? Very, very important. So it's pretty amazing to me that they were able to do what they could do with that big constraint there of not having a temporal element, really, at least not explicitly in the way that they do now in the new work. But also, I think, just even at this stage, it's impressive just how quickly it's able to come up with all of this stuff. And then again, also just to point out, all this machine learning neural network stuff is all done with probabilities, and so those are the numbers that you're seeing there on the left, as those are probabilities, right?
Here you can see predictions of the stop signs, the stop lines, the lines, the edges, the cars, the traffic lights, the curbs here, whether or not the car is parked, all of the static objects like trash cans, cones, and so on, and everything here is coming out of the net, here in this case, out of the Hydra net. So that was all fine and great, but as we worked towards FSD, we quickly found that this is not enough. So where this first started to break was when we started to work on Smart Summon. Here I am showing some of the predictions of only the curb detection task, and I'm showing it now for every one of the cameras. Now the problem is that you can't just directly drive on image space predictions. You actually need to cast them out and form some kind of a vector space around you. So we attempted to do this using C++ and developed what we call the occupancy tracker at the time. So here we see that the curb detections from the images are being stitched up across camera scenes, camera boundaries, and over time.
All right, so here I think very clearly you can see how this is not good enough, right? I mean, just looking at that top-down view, this is the representation of what the car thinks the world looks like. It's not going to cut it. I did a video actually where I tested Smart Summon. You can see just how poorly it performed, right? It's a much more difficult problem than the highway problem.
We very quickly discovered that the image space is not the correct output space. You don't want to make predictions in image space. You really want to make it directly in the vector space. So here's a way of illustrating the issue. So here I'm showing on the first row the predictions of our curbs and our lines in red and blue. And they look great in the image, but once you cast them out into the vector space, things start to look really terrible. And we are not going to be able to drive on this. So you see how the predictions are quite bad in vector space. And the reason for this fundamentally is because you need to have an extremely accurate depth per pixel in order to actually do this projection. The other problems with this, by the way, is also for object detection. If you are only making predictions per camera, then sometimes you will encounter cases like this where a single car actually spans 5 of the 8 cameras. And so if you are making individual predictions, then no single camera sees all of the car. And so obviously you're not going to be able to do a very good job of predicting that whole car. And it's going to be incredibly difficult to fuse these measurements. So
at the beginning, they were basically applying the problem to each image separately, each of the 8 cameras, and then fusing it together, which, as you can see, resulted in the fact that it could not map out the world very well, even though it was optimizing the problem very well for each image of the 8. Then when you put it all together, the result was far less than what we would desire. So now what they do is they fuse all of the cameras first together and then generate predictions based off that fused thing.
We have this intuition that what we'd like to do instead is we'd like to take all of the images and simultaneously feed them into a single neural net and directly output in vector space. Now this is very easily said, much more difficult to actually achieve. So there are 2 problems with this. Problem number 1, how do you actually create the neural network components that do this transformation? And you have to make it differentiable so that end-to-end training is possible. And number 2, if you want vector space predictions from your neural net, you need vector space data sets. So just labeling images and so on is not going to get you there. You need vector space labels. So here are some of the results. So on the left, we are seeing what we had before, and on the right, we're now seeing significantly improved predictions coming directly out of the neural net. This is a multi-camera network predicting directly in vector space. And you can see that it's basically night and day. You can actually drive on this.
So this is, I think, really, really impressive. I'm not sure what the state of the work is that other companies are doing, but this is pretty wild that they were able to do it. They took the 8 cameras, turned it into just one large input after some processing, and then we're able to come up with a representation of what the world looks like with a strong degree of confidence, as you can see there.
This also improved a lot of our object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue. And basically, if you can't predict these cars if you are only seeing a tiny sliver of a car. So your detections are not going to be very good, and their positions are not going to be good. But a multi-camera network does not have an issue.
Okay, so this is another one where it's pretty naive to think that this is going to work before when they were processing each image individually. It's when you have vehicles or anything really that crosses from the view of one camera to another, then of course the car can get confused, right? Or like if it's a semi where it's covering up like your entire side, and part of what the forward cameras can see and maybe a little bit of what the rear camera can see as well, it's not going to know what's going on very well. But if we're able to look at the whole scene 360 and then process that, then obviously we're going to have a much better sense of what's going on around us. So now we're looking at the whole world, but we're still looking at it on a frame-by-frame basis. And so the part that needs to be added here is then the temporal element.
Okay, so at this point we have multi-camera networks, and they're giving predictions directly in vector space, but we are still operating at every single instant in time completely independently. So very quickly we discovered that there's a large number of predictions we want to make that actually require the video context, and we need to somehow figure out how to feed this into the net. So in particular, is this car parked or not? Is it moving? How fast is it moving? Is it still there even though it's temporarily occluded? Or for example, if I'm trying to predict the road geometry ahead, it's very helpful to know if the signs or the road markings that I saw 50 meters ago. So we try to develop, we try to insert video modules into our neural network architecture, and this is kind of one of the solutions that we've converged on. So we have the multi-scale features as we had them from before, and what we are going to now insert is a feature queue module that is going to cache some of these features over time, and then a video module that is going to fuse this information temporally. And then we're going to continue into the heads that do the decoding. Also, in addition, notice here that we are also feeding in the kinematics. This is basically the velocity and the acceleration that's telling us about how the car is moving. So not only are we going to keep track of what we're seeing from all the cameras, but also how the car has traveled. So here's a cartoon diagram illustrating some of the challenges here. There's going to be the ego car is coming from the bottom and coming up to this intersection here, and then traffic is going to start crossing in front of us, and it's going to temporarily start occluding some of the cars ahead. And then we're going to be stuck at this intersection for a while and just waiting our turn. This is something that happens all the time. And so if a car gets temporarily occluded, then the neural network now has the power to look and reference the memory in time and learn the association that, hey, even though this thing looks occluded right now, there's a record of it in my previous features, and I can use this to still make a detection.
All right, so that's really, really big and should be obvious. If you've driven at all, it's very, very important to remember all kinds of things about the scene, right? The context that you're in, from a second ago, 10 seconds ago, a minute ago, because there's two elements, right? One is time and then one is distance. So for things like a lane marking, the distance is really important, right? Like if I'm in a left turn only lane, like that shows up, 30 feet back, and then regardless of what speed I'm traveling at, like that's when that began, and I need to know, hey, I'm in a left turn only lane. All right, that's one thing. And then the other thing is, when objects get basically blocked in their view, as he says, occluded, then we're talking about a time element. We're knowing, like, okay, before I was able to see this thing, now it's being blocked, but it's probably still back there, and based on what's going on and the way it was moving, this is probably where it is. So the two big mistakes were processing each image individually instead of as a whole. And then there's the vector space stuff, which is really cool and important as well. And then now adding in this element of time, of holding some stuff in memory, and then also actually processing video. So it's processing video clips, not just individual images. To me, and I haven't really had a time to think too much about this specifically, but to me it seems like as long as you can cache some of these things for like minutes on end, right? Which you can, because it's not that much information to sit, like remembering I'm in a left turn lane, right? That's not a lot of information. So it's not hard to hold on to that over time and inject that, right, into my decision making. So that's what they're doing, and then processing the video. I'm not sure how many frames and how much time is the unit of data that gets pushed into the video net, right? That I'm not sure about. But if you think about it, I don't think it needs to be that long. It's much more important, like the video will give you a sense of acceleration, deceleration of things, right? What it gives you is the change in the scene from one frame to the next. And that's really, really useful. But what's more useful beyond just a few seconds or so, I'm not sure what the right time frame is again caching and remembering those important things about the scene, of like what kind of a lane am I in, where are the cars around me, how many are there, that kind of thing. Like, is there a traffic light? What color is it? These kinds of things are more important to, I think, hang on to. Well, maybe not the traffic light, because you'd see it. Yeah, probably not. But you know what I mean. There's like these things that are important to hang on to, and I don't think that they're all that data intensive to hang on to, which is good. So I don't think that the video, the chunk that needs to be processed each time needs to be all that long, probably.
Suppose you're trying to make predictions about the road surface and the road geometry ahead, and you're trying to predict that I'm in a turning lane and the lane next to us is going straight. Then it's really necessary to know about the line markings and the signs, and sometimes they occur a long time ago. And so if you only have a time-based queue, you may forget the features while you're waiting at your red light. So in addition to a time-based queue, we also have a space-based queue. So we push every time the car travels a certain fixed distance.
So he's just saying what I was saying a little bit ago. So I think what we'll do is kind of fast forward a little bit. All right, so here's a little bit more about the video processing. And he gets super technical again. A lot of this was designed to be a recruiting effort and to get people that really know a lot about it super excited and want to join the team. So there's all this really technical stuff, but essentially they have these spatial recurring neural nets, which he calls RNNs. One of the things about the neural nets is that, again, the jobs are kind of broken down. So like you can have some that's just looking, again, like I talked about earlier, about the boundary between objects, like where does one object end and another begin. Like you can look for all these different sort of features of the image, or in this case the video. And I think that's something that our brain does too, like just to some degree, that it's, different parts of it are probably figuring out different things about what's going on. Actually, definitely. But the result coming up here in a moment is going to be the result of these spatial recurrent neural nets, each one of them kind of showing some different aspects of it that it was looking for.
It's a spatial recurrent neural network video module. And so what we're doing here is, because of the structure of the problem, we're driving on two-dimensional surfaces, we can actually organize the hidden state into a two-dimensional lattice. And then as the car is driving around, we update only the parts that are near the car and where the car has visibility. So as the car is driving around, we are using the kinematics to integrate the position of the car in the hidden features grid. And we are only updating the RNN at the points where we have that are nearby us, sort of.
What's actually really smart is, again, the name of the game here, and a lot of it, is going to be efficiency. Anytime that there is data that's constant across decision-making points, or really across any point in the process, right, then you can essentially forget about it. Well, not forget about it, but just treat it as constant, and you don't have to reprocess it and rethink about it. So here what Andre is saying is that just the things it's able to get new information on are the things that are going to be updated, and then it's going to make some assumptions about everything else, instead of expending processing power on those things again, which would make no sense. And by the way, when he talks about when he says expensive, right, that's basically, it can mean like it's expensive in a lot of ways, right? It's inefficient, it takes processing power, it takes time, like just, yeah.
Here what I'm going to show you is the car driving around, and we're looking at the hidden state of this RNN, and these are different channels in the hidden state. So you can see that this is after optimization and training this neural net. You can see that some of the channels
Yeah, so again, these are different featured channels.
Keeping track of different aspects of the road, like for example, the centers of the road, the edges, the lines, the road surface, and so on. Here's a few predictions that show what this looks like. So here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. So we're only showing a few of the predictions here just to keep the visualization clean. And this is only showing a single clip, a single traversal, but you can imagine there could be multiple trips through here, and basically a number of cars, a number of clips could be collaborating to build this map, basically and effectively an HD map, except it's not in a space of explicit items, it's in a space of features of a recurrent neural network, which is kind of cool. I haven't seen that before.
So essentially what he's saying is that for any place that the cars have traveled by, they've cataloged all of the features that they've identified, right, probabilistically through the processing of the car. And then if multiple cars come through that area from different directions or what have you in different lanes, then you can essentially aggregate all that data together. So if you scale that up to all of Tesla's network, traveling across all of the, one country and then now many countries later, you've got huge amounts of data about all kinds of things, all of the different features that it's collecting, like what's the road surface like, where are the curbs, what kind of lanes are there, where are the traffic lights, but way more than that. Like, they can add in trees and buildings, and essentially later they could have a really great understanding of the world everywhere that Tesla cars go. This is not a small thing. That's really kind of crazy. And again, unlike say a LiDAR map, which will just give you surfaces and depth. I guess the LiDAR mapping would just give you where stuff is. This is more a map of concepts. It's hard to put into words, but it's really cool. It could be very useful in the future as a source of data. That's really wild.
We fuse the multi-scale information with BiFPN. This goes through a transformer module to re-represent it into the vector space in the output space. This feeds into a feature queue in time or space that gets processed by a video module like the spatial RNN, and then continues into the branching structure of the HydroNet with trunks and heads for all the different tasks. And so that's the architecture roughly.
All right, so here what I want to point out is the bottom set of videos. So we've got 5 videos there. So the I don't know if you'd call it a feature, but the thing that thing is trying to figure out is depth. Tesla cars used to use radar, and there was some concern about, when we remove the radar, how good is depth perception going to be. Radar had problems when you would go under a bridge. There's a point where the bridge is kind of in front of you, and the radar would ping back from the bridge, and it looks like, hey, you're about to hit a wall. But then as you get closer, then of course that bridge is now overhead, and the radar signal can travel right through and doesn't bounce back. That was one reason why there was phantom braking in the past. There was concern about whether or not we'd be able to sense depth using just video. And we'll see here that actually they were able to do a really good job of that, which makes all the sense in the world. We've got 2 eyes, the car's got 8, right? It's got 3 different forward-looking ones. So, and really, beyond like right here, you can get a really good idea of depth with just 1 eye as well. Like not nearby, that if you're trying to manipulate things, it can be a little tricky if you've got 1 eye closed. But stuff that's further away, you can get a very good sense of depth, just because of the parallax nature of things, just using 1 eye or 1 camera.
So definitely, this architecture has definitely complexified from just a very simple image-based single network about 3 or 4 years ago and continues to evolve. But this basically is how you achieve a very nice vector space. And now I believe Ashok is going to talk about how we can run play and control on top of it.
All right, so what we've done so far is we've figured out how does the car understand what's going on around it. And like we've generated basically this vector space that gives us our understanding of the world around us and what's going on. And then now, of course, we need to then decide what the car should do. So that's what this guy's going to talk about.
Thank you, Andre. Hi, everyone. My name is Ashok. I lead the planning and controls, auto labeling and simulation teams. Like Andre mentioned, the vision networks take dense video data and then compress it down into a 3D vector space. The role of the planner now is to consume this vector space and get the car to the destination while maximizing the safety, comfort, and the efficiency of the car. Even back in 2019, our planner was a pretty capable driver. It was able to stay in the lanes, make lane changes as necessary, and take exits of the highway. But city street driving is much more complicated.
Now here's a part that really blew me away that I didn't, that I had no idea And of course it makes sense. When I'm driving, I have in my head an idea of what other vehicles are doing and are set to do, right? Like when someone really simple example, someone puts their turn signal on, then you know they're going to turn, you're watching their speed, and as they take that turn, you have a sense of the timing, right? How long it's going to take for them to actually execute the turn, get out of your way, and so you adjust your speed so that you'll be able to keep going near the highest speed that you could without hitting them, right? So obviously a full self-driving car is going to need to be able to do a similar thing. Not just planning for what other cars are going to do or where they're headed, but also for pedestrians, any other objects that could be a problem for us. And so here we learn, which is really, really cool, is that how that works, that it actually plans for everyone.
It's important to not just plan for ourselves, but instead we have to plan for everyone jointly and optimize for the overall scene's traffic flow. In order to do this, what we do is we literally run the autopilot planner on every single relevant object in the scene. Here's an example of why that's necessary. This is a narrow corridor. I'll let you watch the video for a second. Yeah, that was autopilot driving in a narrow corridor, going around parked cars, cones, and poles. Here there's a 3D view of the same thing. The oncoming car arrives now, and autopilot slows down a little bit, but then realizes that we cannot yield to them because we don't have any space to our side, but the other car can yield to us instead. So instead of just blindly braking here, autopilot reasons about that car has low enough velocity that they can pull over and should yield to us because we cannot yield to them, and assertively makes progress. A second oncoming car arrives now. This vehicle has higher velocity, and like I said earlier, we literally run the autopilot planner for the other object. So in this case, we run the planner for them. That object's plan now goes around their side's parked cars, and then after they pass the parked cars, goes back to the right side of the road for them. Since we don't know what's in the mind of the driver, we actually have multiple possible futures for this car. Here, one future is shown in red, the other one is shown in green. The green one is a plan that yields to us. But since this object's velocity and acceleration are pretty high, we don't think that this person is going to yield to us, and they're actually going to go around these parked cars. So autopilot decides that, okay, I have space here, this person is definitely going to come, so I'm going to pull over. So as autopilot is pulling over, we notice that that car has chosen to yield to us based on their yaw rate and their acceleration. And autopilot immediately changes its mind and continues to make progress. This is why we need to plan.
All right, and here I have to say, I don't know about you, but you've ever played that little dance, right, with another pedestrian coming your way, and you're like, I'm going to go left, you're going to go right, who's going to go which way? The same kind of thing happens on the road too sometimes, right? And I think already in this space, we're seeing how the AI here, the neural nets, can be smarter than we are in terms of projecting based on their speed and everything, like where they're likely to go, what are the different possibilities, and also very quickly evaluating, like, okay, what you're seeing there is like, okay, if they don't yield to us, where do we need to stop so that they can then come around us safely and still get where they want to go? So I need to have an idea of like how big that vehicle is, how big the space is, right? This is something that's at least hard for me to do very, very quickly. So I'm really quite impressed that it could do that. That's really amazing. Now, they didn't get into that about object dimensions and all that stuff, but it looks to me like it's got a pretty good sense of that stuff going on. I don't know, they haven't gone into too much detail, but it looks like that's really happening.
For everyone, because otherwise we wouldn't know that this person is going to go around the other parked cars and come back to their side. If we didn't do this, autopilot would be too timid and would not be a practical self-driving car. So now we saw how the search and planning for other people set up a convex valley. Finally, we do a continuous optimization to produce the final trajectory that the planner needs to take. Here, the gray thing is the convex corridor, and we initialize a spline in heading and acceleration, parameterized over the arc length of the plan. And you can see. All
right, so he's gonna use a lot of $10 words to talk about this, but essentially, what's good to know about the way that the car plans what to do is it's optimizing for a number of things, right? So we can see here what those things are. One is how long it's going to take to make the maneuver, right? We want to obviously, shorter is better, right? But then of course the most important one is in the bottom left, that's collision risk. So we definitely don't want to get in a crash, right? So we want to minimize the chance of a crash. And then the other things that we have are jerk and acceleration, right? So it looks like lateral, so to the side. In other words, these are measures of potential discomfort for us in the car. It's like getting thrown this way, right? Point being that it's trying to optimize for comfort, safety, and time. So those are the three things that it's optimizing for all the time, which is really, really cool. And I bet you that, of course, collision risk has huge weight compared to all the other ones, as a function of the total cost, which is in the top left. All right, there's a lot of other cool stuff that's going on. Some of it's just too in the weeds to get into. Their main point here, I think, is that the world is very complex, and they are coming up with ways to figure out how to tell what the car should do in those scenes. And it can be so messy. Like here I'm looking out. I've got clear lanes that are made with reflectors, so it's really easy to see where they are at night. Like the road surface is incredible. You know what I mean? Like, yeah. But that's not the world everywhere. And so this is a scene from somewhere in India where we've got a roundabout with many different types of vehicles, no lane markings, really messy situation. Car needs to be able to handle that too, right? So it's going to have to track all of these objects and where they're going, and all that stuff, all of the ones that are important anyway, in vector space. And so that's the goal, and it's going to be able to determine what the best thing to do is, again optimizing for what everyone is doing and what we're doing in order to ensure our safety and then also comfort.
It's a crazy world. We can try to scale up these methods, but it's going to be really difficult to efficiently solve this at runtime. What we instead want to do is use learning-based methods to efficiently solve them.
All right, and then the way that they're going about solving these issues is again leveraging the power of machine learning. So instead of basically writing discrete instruction set, which in really simple scenarios can work, they're going to be using a pretty smart method of machine learning that he talks about here, and he illustrates with just parking a car, and how if you use sort of really brute search heuristics, it's very expensive, it's very, very slow, and really just not at all the way to go. And there are ways to really cut out a lot of that problem and apply machine learning in order to get us to the solution much faster.
Parking problem, but still illustrates the core of the issue. Here, this is a parking lot. The ego car is in blue. The vision networks produces vector space, and we have cars moving around in it. This basically looks like an Atari game, and it's a multiplayer version. So we can use techniques such as mu0, alpha0, etc. that was used to solve Go and other Atari games to solve the same problem. So we're working on neural networks that can produce state and action distributions that can then be plugged into Monte Carlo tree search with various cost functions. Some of the cost functions can be explicit cost functions like distance to collisions, comfort, traversal time, etc. But they can also be interventions from the actual manual driving events. We train such a network for this simple parking problem. So here again, same problem.
And as we can see, it's a whole lot more efficient. So real quick, it took almost 400,000 tries using just the Euclidean distance to the goal search heuristic, which is really, really dumb, right? It's just, yeah. And then they added a little bit of navigation information to it, and they were able to cut that down drastically to 22,000. But now we're, a couple more orders of magnitude down to just under 300 tries for this neural network heuristic approach using this Monte Carlo stuff. So really, really cool. If you simplify the problem down to vector space and you apply neural networks, you can end up with a really good solution. Before we move on to other parts of the presentation, I think we can summarize by saying that as time goes on, the explicit coding of command and control, so what the car should do, this planning and control stuff, will be replaced with end-to-end neural networks. Right, that's the goal, and I think we all knew that was going to be the way it was going to have to be, right? I don't have in my head like the set of instructions and a checklist for every problem that I go through. It's like, oh, okay, if you end up with scenario, 537B, then you follow like instruction set Z. You know what I mean? Like, that's never ever going to work. I need to have just this kind of way of thinking about things that's just ready to go for whatever problem I encounter. And so that's why the end-to-end is really going to be the way to go.
And it can be optimized end-to-end, both with explicit cost functions and human intervention and other imitation data. This then goes into explicit planning function that does whatever is easy for that and produces the final steering and acceleration commands for the car. With that, we need to now explain how we train these networks.
So now here's where we're going to zoom back out of the car. So far we can kind of, it's not really that simple, or that clean of a distinction, but we can kind of think of it as we were looking at everything that's going on just within the car, right? The car has the cameras, data coming in. We have the hardware, which converts it to the vector space, right? It's running all these different neural networks and figuring all this stuff out, and then the output is it decides what to do. But again, that neural network, basically the software that's on the car, is getting updated from Tesla over the air. Now, how do we generate the best software, right? That's what they're going to talk about now, is about how to train. So again, you can have a much more complicated computing going on at Tesla headquarters, right, wherever that might be, in order to generate the software, right, the neural network that we then ship off to the car. So we can have a whole lot of complexity at this headquarters level, the training level, compared to the test level, which is the level on the car, right? Yeah, so that's what they're going to talk about now, and that's another place where I'm really impressed at where Tesla is. It's really, really quite amazing. I'm really impressed in what they're doing in 3 areas that are all really connected. So the first thing they talk about, and I don't know that it really makes all that much sense to like watch the video so you can see how this happens, but as you know, as you've learned by now, the neural network makes predictions about things, and it'll make predictions about what things are, right? Like, is that the curb? Is that a lane line? Is that a car? Is that a dog? Is that a human? And so in order for the neural network, the machine learning to happen, like in order for it to get better, you need to tell it when it's right, right? And so that can be very, very time-taking if you've got to do it manually. If you've got to say in each single frame, for instance, yes, this is a cone. Yes, this is a dog, right? But it's not just like, yes, this is a dog. You have to go in there. You have to, basically outline exactly the cone and say this is cone, right? For every single frame. It's huge amounts of labor. It's ridiculous. But you need that in order for it to like say, okay, I had this prediction based on the network at the stage. Was it right or not? If it was right, then we can change some weights in order to improve the prediction next time, right? So that's the whole iterative process of improving the network of the machine learning. Obviously what we want then is a way that's very, very much more efficient in terms of labeling. And so what they've developed are tools. First, they developed tools for labeling using video. So like there was some sort of persistence of objects across time, and then they were much more, it was much easier to label things, so it wasn't frame by frame anymore. So that was a huge help. But then on top of that, now is just auto labeling, is leveraging their I think 10,000 GPU cluster in order to generate labels automatically. I think Andre called it Operation Vacation at some point. But the idea is that if they could get their computer, like their, right now it's a GPU cluster, but if they can get their computer at headquarters to be so smart that it can automatically label everything, then they can just go on vacation. It'll label all the stuff, and then it'll run the network and train end to end against the new data, and then it'll improve, and then it'll label more new data coming in, more new clips, and then so on and so forth until it gets perfect, right? And so they can just go on vacation, and this thing will get smarter and smarter on its own. So that was the project. So at the very least, let's look at what some of that looks like. So hold on, let's go back to the way things were done manually, which is a giant pain, I think here.
Yes, and this is what it looked like, where we are sort of drawing polygons and polylines on top of these single individual images. As I mentioned, we need millions of vector space labels. So
giant pain in the butt. And then here we have
labeling in vector space, not in individual images. So here what I'm showing is a clip, and you are seeing a very small reconstruction. You're about to see a lot more reconstructions soon, but it's a very small reconstruction of the ground plane on which the car drove, and a little bit of the point cloud here that was reconstructed. And what you're seeing here is that the labeler is changing the labels directly in vector space, and then we are reprojecting those changes into camera images. So we're labeling directly in vector space, and this gave us a massive increase in throughput for a lot of our labels, because you label once in 3D, and then you get to reproject.
Yeah, so that was also another huge leap. But let's look at the auto labeling, which is really, really cool.
So even though we have lots of human laborers, the amount of training data needed for training the network significantly outnumbers them. So we try to invest in a massive auto labeling pipeline. A clip is an entity that has dense sensor data like videos, IMU data, GPS, odometry, etc. These can be 45 seconds to a minute long. These can be uploaded by our own engineering cars or from customer cars. We collect these clips and then send them to our servers, where we run a lot of neural networks offline to produce intermediate results like segmentation masks, depth, point matching, etc. This then goes through a lot of robotics and AI algorithms to produce a final set of labels that can be used to train the network. So a single car driving through some location can sweep out some patch around the trajectory using this technique. But we don't have to stop there. So here we collected different clips from the same location, from different cars maybe, and each of them sweeps out some part of their road. Cool thing is we can bring them all together into a single giant optimization. So here, these 16 different trips are organized aligned using various features such as road edges, lane lines. All of them should agree with each other and also agree with all of their image space observations. Together, this produces an effective way to label the road surface, not just where the car drove, but also in other locations that it hasn't driven yet. We don't have to stop at just the road surface. We can also arbitrarily reconstruct 3D static obstacles.
Okay, so here this is what's called a 3D point cloud. So this, I think, gives you a very clear demonstration of the fact that absolutely you can use cameras to determine depth, and you can do it really, really well. This is quite impressive to me.
Here, this is a reconstructed 3D point cloud from our cameras. The main innovation here is the density of the point cloud. Typically, these points require texture to form associations from one frame to the next frame. But here, we are able to produce these points even on textureless surfaces like the road surface or walls. And this is really useful to annotate arbitrary obstacles that we can see in the world.
Okay, so basically they figured out a way to, again, do the labeling at Tesla headquarters, so not on the vehicle, and they're able to use that to rapidly improve, well, not that rapidly, but fairly rapidly, use it to train the network and improve it. So that's really, really cool. And one of the applications, of course, one of the big challenges they had was to remove radar. So there was, I think, there was a part shortage with radar, but there was also the understanding that radar was actually becoming more of a problem than a help. Because there's some differences in the radar signal versus the vision, where they could sometimes conflict with each other. And really, like, I don't have a radar, right? And I can drive. So what we really wanted was just to go based off of vision alone. So within just a period of 3 months, they were able to train the network to match the performance of when we were using radar without radar, which is pretty incredible, pretty cool. In this case, they're talking about how to tell where cars are that are in front of you that are being hidden by the spray from a semi that's coming by.
Removed it in a very short time span, I think, within 3 months. In the early days of the network, we noticed, for example, in low visibility conditions, the network can suffer understandably, because obviously this truck just dumped a bunch of snow on us and it's really hard to see. But we should still remember that this car was in front of us. But our networks early on did not do this because
All right, and then I think the last point before we move on from the labeling section of the talk is this one: is that there's they have huge amounts of data. Tesla has, because there are hundreds of thousands of cars out there now in the fleet that are sending back this data, and so if they can get the auto labeling working on their GPU cluster, then they can just feed in loads of data. It'll auto label for this new thing that they want to improve upon, right? Whatever it might be, some particular scenario or thing, and then bam, they have ridiculous amounts of data to train on. This is a huge advantage that no one else out there has. No one else out there has the richest of data that they can just we want to fix this problem, source loads of data, video clips from all these cars, all 8 cameras, bam, label, train the network, and then ship the update back out on the new, the next trained neural network. Just totally wild. All right, so that's enough about labeling. The next section is about what you do when you just don't have enough of the real world scenarios in order to train with, right? And that's because there's some really, really weird stuff that'll happen out there that the network needs to be able to handle, the neural net needs to be able to handle, that it just doesn't happen enough for it to train. It's kind of, the thing about neural nets is something to know about them is that it's not like a human yet, where you can say, hey, that's a fire hydrant. And from there on out, us humans are like, okay, that's a fire hydrant, right? We can see it from different angles, and it can be different colors and in different places and scenes, and we know that's a fire hydrant. Neural nets don't work like that. You need to feed them loads of fire hydrants of all different shapes and colors and tell them, hey, this is a fire hydrant, and then it'll guess, and it'll be, sometimes it'll think like, well, that could be a potato, I don't know. You have to say, no, that's a fire hydrant. But eventually it converges upon what a fire hydrant is. So it's very different, this machine learning, from the way we operate to some degree. That's one part that I think, I don't know for sure. Maybe, well, anyway, that's something I'm keen to see if they can improve on that in terms of a synthetic brain, whatever that looks like, sort of this generalized AI, whatever the hardware and software for that might look like in the future. But anyway, for now, this is what we got. So if we want to have these edge cases, these weird things, show up and train on them, then one way to do it is to make them. And so that's to generate a simulation that has is as close to the real world as we need in order to train the network. The closer we get, the better. And so they've done that. They've built some really cool simulation tools that look like the best photorealistic games that are out there. So we'll look at a brief clip of that and then move on. But just to say that, yeah, this is where they can make some really weird things happen in simulation, and the simulations are really, really high fidelity. They're very, very good.
So yeah, in addition to auto labeling, we also invest heavily in using simulation for labeling our data. And since this is simulation, it starts from the vector space, so it has perfect labels. We need to render the visuals in a realistic manner. You cannot have what in the game industry called jaggies. These are aliasing artifacts that are a dead giveaway that this is simulation. We don't want them. So we go through a lot of pains to produce nice spatiotemporal anti-aliasing. We also are working on neural rendering techniques to make this even more realistic.
Yeah, so this is pretty cool. You can see how much fidelity we have. On the left is the real clip, and then on the right we have the recreated sort of the simulation of it. Very, very cool. But yeah, just compare the left and the right, and I think you really get a really good sense of how good their simulation tools are.
Not just that, we can use neural rendering techniques to make it look even more realistic. So we take the original video clip, recreate a synthetic simulation from it, and then apply neural rendering techniques on top of it, and it produces this, which looks amazing in my opinion, because this one is very realistic and looks almost like it was captured by the actual cameras.
Yeah, so they've done a really, really good job. And as you can imagine, in order to do all of this, right, to do all the auto labeling, to run the simulations, and then to train the neural networks, then you need a whole lot of computing, right? And so that's where we come to one of the most amazing things that was presented at Tesla AI Day, which is their progress in creating computers. So they already made the FSD computer, the hardware 3 that goes in the car, right? That was their own design, and that was really, really cool. But right now, for the at-home stuff, the GPU cluster is just a GPU cluster. Like, they're buying video cards, on the market. It's not their own thing. And so now they're developing their own hardware for that. That's what's called Dojo, which is a reference, of course, to the Matrix, where plug in to the Matrix and like you could be uploaded a new program, and in the Dojo you would learn how to use Kung Fu, or like how to jump over buildings or whatever. All right, so in terms of Project Dojo, I don't think it's important for us to get too much into the weeds with the technicalities of it for this video. I just really want to talk about what it is and what it means. And so this is their chips that they've developed, right? This is their silicon. What you should know about it is it's very small, very fast, and doesn't consume all that much power. So it's a 7 nanometer scale technology. That's as small as we're currently producing silicon. And it's very, very fast, as you can see. So this is at 16 and 8-bit using different methods. It can do 362 teraflops, or tera operations per second. It can do 22.6 at 32-bit, it looks like. Oh, this is the bandwidth for information transfer. So that's how fast it can think, and the teraflops. And then the bandwidth for information transfer, 10 teras like within the chip itself, and then 4 terabytes from chip to elsewhere, right? So pretty cool. And then its total power draw is 400 watts. So that's how much power this little deal, which is pretty impressive, needs. But of course, that's not it. This is the crazy. So first, it's real. They've built it. We can see it here in this image, right? So this is actually something that they've got. But then on top of that, they've figured out a way to scale this stuff, which is what you need, obviously, right? Currently, we just put a bunch of video cards together, but they found a way to scale this up. And so the next level up from this D1 chip is what's called their training tile, which has 25 of these. And each one of them, as you can see here around their edges, has an input-output that's basically just where information comes in and goes out from the tile, that have a 9 terabyte a second transfer capacity, or bandwidth. So it's interesting that that's actually faster than the transfer rate from one D1 chip out, right? We saw before that the bandwidth out was 4 terabytes a second, but now we have a grouping of 25 of them, and then the transfer rate out from there is 9 terabytes a second. I think the next really big innovation here is that they've integrated power, input, output, and cooling all very effectively in a 3D package for this training tile. And so that's what we can see right here. So this is the full thing. Maybe we can see a schematic of it. 1 second. Yeah, here we can see where we have the computing. And so this tile of the 25 D1 chips does 9 petaflops. So very, very fast, right? 36 tera a second input-output bandwidth, and it's smaller than a cubic foot, right? And then you can see here it's got really good cooling capabilities. That top there, you can hook up to liquid cooling, and then the liquid will pull the heat right out. So very, very cool. But of course, we're going to put many more of these tiles, right, into a matrix. So here we can see that it's going to have a 2x3 set of tiles in one tray, and then 2 trays per cabinet, right? And then we can scale it up further, right, to have multiple cabinets. So each cabinet, we're looking at 100 petaflops, 12 terabytes a second, a section bandwidth. And then we can put that all into an exapod, and this pod that has 3,000 of the D1 chips. But of course, and this is something I haven't seen anyone else talk about here, that when you use the word pod, it's a very modular type of term, right? And it means that they're not going to be constrained necessarily to one, right? So I don't know how many exapods there's going to be in Dojo. Maybe they start with one exapod, but there's nothing about the naming that makes me think that they're not thinking about a multiple exapod solution here in the end. So really, really kind of amazing here on the scalability, right? So this whole thing's pretty wild. So they have all this really technical stuff about how all of this works together and how flexible the system is to run different problems. So it's not just, obviously, right? This should be very obvious. You don't just throw the FSD problem at it. You can throw any other kinds of neural network training problems at this thing, and it's very flexible to how much of the hardware that you need to use at a time. Essentially, the basic building blocks are you need the chips to do the processing, you need some memory, right, to hold on to information, transfer it, and then you need host controlling as well. So that's what's going on here. So yeah, really, really super impressive solution that's using PyTorch, very common in machine learning and AI type of work. Relatively easy language to learn as well, Python. So that's a nice thing. And so here you can see all levels of that, right? You've got the chip, you've got the tile, you've got a cluster of compute, and then you have the software on top of it that helps make it run, and that will allow you to then, if you're another third party, and you want to train some neural networks, right? You could probably license it out, kind of rent some space and do that. So pretty cool. And so now we come to the final part of the presentation, which is about the humanoid robot that Tesla has. And so I think here is probably a really good opportunity for me to kind of recap what the breakdown of the FSD part of it is before we move on to the Tesla bot and then the implications of this whole thing, because those two really go together. To step back, we had some missteps that led to some global maxima or global minima, depending on how you want to look at the optimization problem, where they were analyzing each camera separately. That was dumb. They had to stitch them together. They learned to do that. And then they had no time element. So they weren't keeping information across time very well, and they weren't processing video clips, which brings a whole nother level of information than just like having a bunch of those stitched frames to process. And then really cool that they're using the vector space as kind of like they boil everything down into the vector space, which is where you then apply the planning and control layer on top of. That's super efficient to do that. And that what we learned is that yes, they have a lot of right now discrete programming for planning and control for CNC, but the goal is end-to-end neural network training to make all those decisions as well, and they're working towards that. All right, so that's all what's going on within the car, and then of course to train the neural network that we update the car with, then we can do a lot of more complicated and larger scale stuff at headquarters with Dojo, which is going to be their new computer system that they're building, totally custom, really impressive. And what this should help do is of course generate all that auto labeling, so that we then can have a ton of data to feed into the network and train it. But also do everything faster. So right now their time frame for updating the network on FSD beta is 2 weeks, roughly 2 weeks, to probably evaluate performance of the current state of things, get some new data, label the data, especially the data that they're interested in fixing, sort of problem areas with it. Then of course run simulations and see how it'll perform against other data that we have, and then when we're confident that it's going to be good and work well, then ship it out to cars. So that's right now about a 2 week time frame. And with Dojo, if it works well, if it does everything the team thinks they could do, I heard Elon talk about like a couple days instead, maybe 2-3 days of being the turnaround time. So it could be really huge, because obviously for computers, they don't care how long it takes, right? But for us humans, it's nice if things happen faster. So yeah, it'll be really cool once they have this up and running to see how quickly they're able then to train the neural networks, and therefore to make progress towards this ultimate goal of end-to-end, an end-to-end stack that does everything for us in terms of the of driving the car. So really keen to see what happens. Really excited. But yeah, that was a lot to cover. So I'm going to stop here, and then I'm going to film separately another segment on the implications and on this humanoid robot. All right, so I needed a break. Turned out to be a full day break, but here we are with part 3 of this video. And we'll be covering really what the implications are of Tesla AI Day. And their planned product unveiling is really a good way to kind of frame that discussion. So this product, as many of you may know by now, is a humanoid robot. They had someone dressed up in a suit come up and dance, and for a moment there, got to thinking, all right, maybe this is actually the thing, and if so, that would be really impressive. But it wasn't. That was just a person in the suit. But the actual bot looks like this. It's 5'8", carries 45 pounds, weighs 125. Supposed to deadlift 150. Very slow at 5 miles an hour, so we can run away from it. Ha ha, Terminator. And it should be able to lift 10 pounds with extended arms. So what's the deal with this, and why the heck did it come up in this presentation? Well, the deal with it is that obviously if you're able to solve essentially perception, which they're doing with the cars, which is ingesting what the cameras are seeing, all 8 cameras, and then processing all of that, as we've seen already with the vector space and everything, then really you could apply that to anything else. It doesn't have to be a car, right? And so one of the big things, of course, for Tesla has been what's called manufacturing hell. Has been their difficulty in ramping up product pipelines, over automating, because the current state of robotics, in many cases, just isn't up to the task. And so that's probably part of what the motivation here is initially, is to replace some of the workforce of robots to do, again, the repetitive and dangerous tasks. Obviously, this one doesn't have a whole lot of carrying capacity or a lot of strength, so it's not able to really surpass humans in that regard. But again, all the places along the assembly line right now are using humans that aren't necessarily superhuman, right? They're definitely not superhuman, so why not, right? So I think that could be really good. And that's kind of the initial place where this can go. And there are a lot of challenges, mind you. So before we get too carried away on how soon this is going to happen, it's a lot more complex to be a humanoid, to have a humanoid robot working, than it is to have a car working, because as we know with the car, the only 2 outputs are the steering and the acceleration, right? Deceleration. So, just those two things to worry about. With a humanoid robot, you're going to have all of the different limbs and appendages, and then all of the balance stuff, right? And so there's a whole heck of a lot to it, right? You've got not just the orientation of the car is pretty simple with a humanoid robot, and you've got the orientation of the neck, the arms, every single joint, right? How all that combines to do balance, and then if you're going to have it do actual physical tasks, which that's the goal, then it's one thing when you can see what are you picking up and grabbing, right? But in order to do that, when you don't have any visibility, then you'll need some kind of other sensors in order to get, say, tactile feedback, to see if you're kind of squishing something or not, and how much pressure you're applying to something. And then also whether or not your limbs are encountering any objects that you can't see. But in any case, it is a much more complicated task in terms of the sensor suite that's required, I believe. And then, of course, in terms of all the actuators. And then one of the big difficulties, depending on the intended task, is going to be battery capacity, right? Because if this thing weighs 125 pounds, then how long is that battery going to allow the humanoid robot to operate? Is that a couple of hours, right? Is that enough? I suppose so. You just need a lot of them. So we'll see. We'll see. I don't know what they can do in terms of the battery tech. I really don't know what it would be capable of doing at that weight with the current state of battery technology. So I'd be really curious to see. But suffice to say, there's a lot of challenges there. But why I bring this robot up in terms of the context of the broader implications of Tesla AI Day is to go back again to where we began this discussion with the context, which was, I believe this is a way for Elon as well as solving a lot of other things along the way, right? The full self-driving for one, all the traffic, all that stuff. It's also a way to regulate or have a say in the development of generalized artificial intelligence, right? So that's one. And if we're able to get, it really, I don't know that you need to have the robots be all that intelligent. I don't think it requires generalized AI for these robots to have a really tremendous impact on the labor force out there. But you may or may not have noticed a trend that we're able to mechanize more and more tasks over time. And so far, we've been able to basically generate new jobs so that people still have jobs out there to do, even though we've mechanized a lot of the jobs that we used to do, right? So, for instance, farm labor is sharply reduced. That's heavily mechanized now. A lot of manufacturing now has been mechanized, right? Famously, things like the printing press or, the cotton mill or what have you. But there's been many innovations that have helped to basically automate tasks. And if I take my work, for instance, I've automated a whole heck of a lot of it compared to my predecessor, just because I've been able to integrate a lot of the work into software and skip a lot of steps, eliminate a lot of redundancies, this kind of thing, right? I could almost fully automate my job, except it's full of a lot of corner cases. I trade in kind of a not all that liquid market compared to some others, and so that poses a real difficulty there. I probably could still code it. I probably could still code my behavior, but it would be hard and risky, so I haven't done that. Also, then eventually the cat will be out of the bag, right? That my job's being done completely automated. But anyway, the point being that it is feasible, especially to me, that once you have generalized AI and you have you have robots that are capable of performing all human tasks, then that has profound implications for the labor market. Essentially, eliminating all of the jobs that we wouldn't want to do or that we can do more cheaply using a robot. So right now, a lot of the robots that we have, they can do things like flip burgers, serve coffee. We have a couple of those that are coming out. They're not great at it, but they're okay. They're getting there. There's some that can lay brick in some very specific circumstances where, again, the job is very repetitive. You don't need to be flexible, right, to the environment. In those scenarios right now, we have robots that can do it. That's why they're good for assembly lines. But right now, we cannot replace, say, a plumber or an electrician with a robot very well. But if Tesla's able to do this, of having a humanoid robot that has the ability to perceive the world around it and interact with it, and essentially perform all the tasks that we can do with equal dexterity and without getting tired, right? Obviously needing to be recharged, but then you can kind of like cycle in robots and what have you. Or if it's plugged in, right? So maybe the idea with the Tesla bot initially, at least in the factory, is they're going to be wired, and then you don't have this constraint about the batteries at all. But later on, you might want some that can like do errands or clean around the house or all that kind of stuff. Whether or not we need generalized AI, I'm not sure. But very, very, to put it in our terms, intelligent robot would be able to replace virtually all of human labor. And so that, again, would have profound implications because, well, right now you get paid based off of the value that you provide to your employer, which is then related to the value that the services that your employer provides is able to provide to society. But then, of course, society needs to have money in order to pay for those products, right? So this is kind of one way to look at how things are. Elon boils it all down to labor in his talk. And economists have been trying to figure out how to distill sort of where the value of anything in the economy comes down to. At some point people thought it had to do with land, which of course doesn't make all that much sense. It is one of the resource constraints or inputs, but yeah. And then then they thought it was labor, but I don't think that's really true. You have a lot of things that are really scalable that can be done. For instance, things that are on the internet, right? That provide a ton of value to a ton of people, but they involve absolutely no labor, right? No, and you can't say that their value is in some way related to the labor that would be taken by a human to provide that, because that's not true, right? Delivering a video to you on the other side of the world, the value of you consuming that video has nothing to do with how much labor would be involved in getting the copy of the video to you if we couldn't use the internet, for instance. So I would disagree with him on the idea that labor is really the end-all unit of the economy. I really don't think that's true. Again, it really has to do, it's much more intractable or hard to get a grasp on than that, and it's much more about what people value as an aggregate. Whatever the market can command, basically, right, has always been what the value of something is, and that fluctuates over time, and it's not a constant. So my point is, though, that having the humanoid robots that can replace all of human labor will really kind of break everything completely down, and it can be a very dystopian scenario if you think about it, because then a lot of people think about these things sort of in isolation of like, oh well, if the robots do all the jobs, then there are no jobs, and then we're going to be unemployed, and it's like, oh, that's terrible. Which that's one part of it that could be terrible. But the part that you might forget is that capital, these robots, is owned, right? And that's going to be a very important thing. So, for instance, I'm a Tesla shareholder. And if Tesla deploys these robots and they replace, increasingly a larger and larger portion of the labor force, right? So, first they replace all of the drivers and truck drivers, right? They'll do that, all the cabs and all the truck drivers. Then they replace all of the people in manufacturing lines, generally, right? Except for the ones that do maybe some higher order tasks like QA or training or, running the robots themselves or what have you. But eventually, as the robots spread their skills to new domains, then all of a sudden basically all the labor is being provided by Tesla bots, right? This is when you take things to the limit, and it doesn't have to be Tesla. There could be competitors, whatever. The point being that whoever owns all of this capital, all of these robots, those are the people that are going to be benefiting, and then that pool of people, Tesla shareholders say, it's going to be way too small, right, compared to the general population. This is a major, major problem. So at some point, if you really take things to the limit, you have a couple of scenarios that can develop. You can have the dystopian scenario where you have like an Uber corporation that runs everything, a little bit like US robotics in the Isaac Asimov novels. And that shouldn't be a surprise that that's not an idea that comes up, because a lot of what Elon does comes up in science fiction books, and a lot of it is in the Isaac Asimov books. Now, obviously, a lot of the books have things in common, right? So space travel and robots and all this stuff, but humanoid robots especially. A big prominent feature of Isaac Asimov books. Also, at one point, the robots ran the economy in some of the books. It depends on sort of which phase you're in, but they had a completely planned economy run by robots, and that's another possible scenario, which is odd, actually. I don't think that really makes any sense, but maybe people do need a sense of purpose, and so that's one of the reasons the sort of planning AI developed that, because they didn't really need the labor, right? Though they outlawed robot labor on Earth in some of the books, or many of the books. What I wanted to say is you could either have this dystopian scenario where there's the Uber corporation that runs everything, and I don't know, or basically everything folds into government, which obviously there's going to be people that don't like that idea. But this is like, if there's no jobs to do out there because a robot can do everything, then a universal basic income is really going to make sense. And that's something that Elon mentioned in his talk.
What happens when there is, no shortage of labor? This is why I think long term that there will need to be universal basic income. Yeah. But not right now, because this robot doesn't work. So we just need a minute.
If we could get there, then I agree that universal basic income is really going to be necessary, and it's something you'd want to have set up as the transition's about to happen, to avoid a lot of societal upheaval. You don't want a lot of people, a large share of the population, very rapidly losing their jobs and being in financial hardship and all this kind of stuff. Hopefully we can steward all of this. And so this whole thing is a big deal. And obviously there's a whole lot of can we actually get there from here to there? But there does seem to be a path. Not to generalize AI, by the way. I don't want to say that. Like obviously, they're going to have the computing power that maybe is necessary. I don't know what the key ingredient is to making that happen. I have no idea. When you go from something that's really really smart in a narrow but expanding range of things, and where you start to get to sort of a synthetic consciousness or close enough that you can't tell the difference. I don't know, or if it even matters that much. But anyway, so that seems a little bit further. But there does seem to be a clear path. Anyway, for disrupting a lot of things in terms of transport, first of all, that involves also trucks, which are a big portion of the labor force. It's and a relatively high-paying job as well, so really problematic to eliminate those truck driver jobs. But then this humanoid robot also to eliminate a ton of other low-skilled jobs. And then AI also has the potential to automate tons of what we've thought of as skilled jobs until now, but maybe in the future we won't think so. Like again, a lot of my job I was able to automate too. So, but yeah, very 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 important implications coming out of this thing. So yeah, that's something to take. It's a sobering thought, also exciting as well at the same time. But overall, I hope this helped a little bit to break things down in terms of AI, to help break down AI Day in terms of the context, what the actual presentation was, and how impressive that technology is to a layman. I'm just a geeky dude. I'm a layman. I probably got stuff wrong. I apologize for that. I tried to do my best. With what I know. I didn't do a ton of research because, man, there's just so much to cover, right? And I just wanted to give you my initial reactions, like, after I'm excited about it. So that's it. If you enjoyed it, well, I hope you enjoyed it. I hope you liked it. If you did, hit the like button. Consider subscribing. Helps out the channel. And I'll see you in the next video.